All right, so today we will continue the discussion on inverse design in photonics, and in particular to give a discussion on another important class of method for this inverse design that's called level set. So as a background, we have talked about a number of different ways that you can define the structure that's required in the inverse design process. In the inverse design process, ultimately, what you are doing is you adjust the dielectric function until you get a structure that has high performance. And we talked about the use of gradient descent in order to create such structure. And in order to use gradient descent, you would need to represent the structure in a way so that it's by a function that's differentiable. So up to this point, we talked about two things. We talked about a topology optimization where we discrete the permittivity on a grid of pixels. And then we continuously adjust the value of each pixel, but we apply filter and projection for feature size constraint. We also talk about shape optimization, where we instead parameterize the certain geometric parameter that describe the boundary of the device, and then the gradient is then applied all the way to these parameters. So, for example, in the waveguide taper example, it could be a coordinate such as the thickness of the dielectric region in each individual slices and so on. So that provide another way to parameterize the structure. Now, today, we're going to talk about a level set method, which is yet another way to parameterize the structure. And in fact, in some sense, you can think of as a somewhat of a sort of an intermediate between the topology optimization and the shape optimization. It tends to produce structure that are more regular compared with the topology optimization, but on the other hand, has a richer set of features as compared to the shape optimization. So the idea of a level set method is to define just a continuous function over space, and then you use that function to define a shape by choosing a threshold when the value of the function crosses that threshold, and that's the boundary of the shape. So let me give an example. So suppose you have a function that's represented, that is a very complicated function, phi as a function of x and y in this case, or a two-dimensional space. Now, and the function value fluctuates below and above 0. And then you choose the threshold to be 0. And you say, whenever this function is above 0, I'm going to set the dielectric function or the permittivity to that of silicon. And if it's below 0, then I set it to be air. And in that case, then this function here, together with the threshold, then define a dielectric structure as indicated by here. So more generally, or more specifically, in what we actually implement in the code, we imagine a function that's a linear superposition of the sum of a Gaussian set of a Gaussian radial basis function. These basis function, each of them is a Gaussian-looking function as defined by the center position and the width. And then we put an amplitude in front of each of the basis function, and we add them up. And that produce this level set function. Then you choose a threshold, and that would define a dielectric structure. So when we apply the gradient method, what we're going to do is we're going to keep these Gaussian radial function, basis function fixed. They're in fact distributed on a grid, on a regular grid in the system. So we're going to keep those basis function fixed, but we're going to vary the amplitude in front of it, the pre-coefficient in front of it, to generate a different structure. So now, as I have been emphasizing throughout this lectures on inverse design, the important challenge in inverse design is to specify constraints due to fabrication requirement. And so, for example, you probably don't want to have too small a minimum feature size due to the constraint lithography. And very typically, you also want a radius of curvature so that of a certain the radius curvature to be sufficiently large so that the structure does not have sharp kink and are smooth enough. And so here, what one can do is to modify the objective function to add the penalty terms that involve these matrices, So let me give an example. So on the left is a structure that's generated by, that one could generate by this level set. Now you can see that the structure has holes on the order of a diameter of 100 nanometer and has a minimum feature size here, the distance between two surfaces here, that's about 100 nanometer, and also has some region here with sharp curvatures, with sharp corners. And so the penalty function that one can construct on the level set function specifically penalize it. So here is the value of the penalty function that constrain the minimum feature sizes. And you can see whenever the minimum feature size become small, suppose you choose a desired minimum feature size of 160 nanometer, whenever the minimum feature size is fall below, you start to see this value of the penalty function start to deviate from 0. Similarly, you can also define a penalty function associated with curvature. Again, whenever you have sharp corners, you can see the value of the penalty function start to show up. So using now, let me show you an optimization example. So in this optimization example, our intent is just to do a compact waveguide splitter. So you take a single mode waveguide, sending a fundamental mode in, and you would like to design a region so that you can split the input wave with as high efficiency as possible into two output waveguide. Since we are going to design this for equal splitting of the input-output waveguide, you can consider a symmetric structure. So this is our initial structure, and this is generated by a particular level set function. And you can see that you have a coupling efficiency that's -6 dB, and with a field distribution like that. Now, so it does operates as a splitter, but it's not a very good one. An ideal splitter would have a 50% of the input into each of the output waveguide, and that gives you a coupling efficiency desired to be -3 dB. So you can just apply the level set function without the fabrication size constraint. And in this case, you get a structure that looks like this, applying the optimization algorithm that I talked about. What I'm showing here is half of the coupling region. So it corresponds to half of the coupling region around here. And this structure has mirror symmetry. So the full coupling region is twice as big as this. And the structure works pretty well. You can see now the coupling efficiency get fairly close to -3 dB. And you have in the picture, very nice equal splitting of the incoming power into that of the two outgoing waveguide. And this optimal structure is reached after about 40 iteration in the gradient descent step. But you see a lot of small features here. So, for example, you see this tiny air hole, tiny silicon regions, and regions with sharp curvatures on the boundaries and so on. So now, instead of doing so, you can combine the level set method, as we talk about, with a penalty function that's specifically designed to get rid of these small feature things and to get rid of the sharp boundary at the silicon air interface. And if you do that, now again, you produce a structure with a performance, in fact, that's not too far from the ideal performance of about -3 dB. And it, as you can see from the picture, it looks pretty well. And you can get to that structure with also about maybe on the order of 40 or 50 iterations. But now you get a structure that are more amenable to nanofabrication. For example, now you only have one hose here, and that's actually pretty sizable. This is about 127 nanometer in size. And here we put in a constraint to get rid of features that are smaller than 120 nanometer. You no longer see those small silicon islands either. And also the interface between silicon and air becomes a lot more smoother. So to summarize what we talked about here, we discussed the level set method, which is another way to parameterize the device design. And as I mentioned, they tend to produce structure that are richer compared with the many shape optimization, but are generally smoother as compared to some of the pixel by pixel topology optimization. And it also, in this case, directly generate a binary structure, consists only of, for example, silicon and air. And it is, I think, also a very useful method to consider as you try to design, try to do inverse design in photonics, for example, in this on-chip. We illustrate this with examples of on-chip integrated circuits, but it's generally quite an important method to think about when you are thinking about doing inverse design in photonics. So with that, let me stop here and thank you for your attention.